the three significant figures. So the change of base formula is as follows. Log base b of x equals log of x over log of b. It also can be used for natural logarithms, which let me go check example 11, see what they use. They do not, they use base. They use this. Okay, this is what they use here. So in your problem, log base 4 of 15 becomes log of 15 over log of 4, like that. So you have to go to that Desmos scientific calculator, which we've been using a lot of lately. And probably want to start with a fraction, and then you just literally type the letters log and then log. So let me snip this in. I'll have you go there as well and enter it, but you essentially enter it exactly the way it's written here, just like this. But you
Okay.
go to the Desmos scientific and see if you can calculate that for us.
That would be 1.953.
Okay, let me take a look here. Did that real fast. Okay, now it says three significant figures. That's a little bit different than three decimal places. That's just three numbers altogether. So 1.995. Is that okay?
Yeah, that's fine by me.
All right. So that's a nice problem, not too long, not too much work to do there. The last problem here is some sort of a, what do we want to call it? Like an application problem again. Apply your knowledge. Okay. Here we go. You snip that in. All right. So it says voltage like pressure appears squared in expressions for power intensity. So by convention, we define gain equals 20 times log V out over V in. An amplifier has an input of 10 millivolts and an output of 3 volts. What is its voltage gain in dB? It's a really complicated way of telling you that voltage in is 10, voltage out is 3. You're calculating the gain, which is 20 times the log, and then the voltage out is 3, the voltage in is 10, like this.
All right.
So you're just putting these numbers back into the formula, and then you're going to Desmos and scientific and then calculating this. Not sure how many significant figures are reasonable. We'll know here in a moment. 20 log. So let me go check the example here. Oh, I'm sorry. So I made a mistake here. The units are not the same. One's in millivolts, one's in volts. So the 10 millivolts has to be converted to volts, or the volts has to be converted to millivolts. It looks like they both convert them to volts. So 10 millivolts, there are 1000 millivolts in a volt. And that changes this number on the bottom here, 10, to become 0.01. So they're trying to get you to use units to make sure you've got the right matching units on the top and bottom. And that does give you a more reasonable answer.
All right. And I got to put that into the scientific.
Yes. Yes.
All right. I put it the same way we wrote it, right?
Yes. Exactly the same way you see it. And let me know what you come up with.
Okay, I got an answer.
Okay. You want to read it out loud for us, please?
Yeah, 49.5.
Yep. And then we want units. The units are decibels, dBs, and that is your answer.
Nice, we did it.
Right.
Okay, let me get a new page ready for lesson number 25. Yeah, 25.
So on to the next lesson. We may need to log back in here. Usually that's the case after a day. All right, you said it 25 graphing logarithms. So we'll probably be using that Desmos scientific calculator. All right, stop and think. All right, here we go. All right, so first question says to state the similarities between log and square root graphs. All right, so what I'm going to do here is graph logarithm and a square root, and we'll look at them together. So here's the square root graph, and then the log one here, graph as well. Okay. Like, do you see similarities between the graphs when you see these? Do you feel like they're similar, they're different? What do
Uh,
you see?
I see a little bit of a similarity. No, actually, no, they're a little different.
Yeah, I actually think they're a lot different. I'm really very surprised they're asking you for this, but we'll do what
Yeah.
they say. We'll do it this way. So if we're looking at sort of a category graph, and then the next thing is domain. Okay. The domain is from left to right. So we're going to do it by, here's the square root graph. Here's the log graph on the right. The domain of the square root graph, I don't know if you can tell, but it stops right there at 0, 0, and it goes to the right forever. Can you tell me the domain from the graph here? This is 0, 0.
I'm not sure what the domain would be actually. Wait, it
So
would
what
be
is the leftmost x value?
0, 4 because that's where like the line is going through the
But so how far right does the graph go?
it goes positive infinity.
It goes forever. Okay, so this is your domain for the log. Now on the, I'm sorry, for the square root, for the log on the right here, this actually goes down forever.
So
But
negative infinity.
well, that would be for range, but for domain, the leftmost x value is 0. And how far to the right does it go, do you think?
Um, it goes in infinite.
Yes. Okay. Range here. So for the square root on the left, what's the smallest y value that you see?
Um, at the for the range for the first graph, um,
Smallest y value,
0, 0.
right? And then it isn't really clear, but this actually goes up forever, even though it looks like it's going more to the right. It actually continues up forever.
So
So the
0,
biggest,
infinity.
yes. Okay. Actually, this one includes that. All right. And then for the log, that's what you're kind of telling me earlier. It goes down forever. It's minus infinity. And similarly to the square root, it does go up forever, just goes really slow, but this actually does go up on the right here does go up forever to positive infinity.
Mhm. So the similarities between the two graphs is that they have a similar domain and range.
Well, kind of. I mean, we're gonna go through all of these, and I guess we'll answer the questions 1 and 2 after we've gotten all of these. So I apologize. It doesn't really have a great flow to it quite yet. We have to sort of um, wait for it towards the end. So the asymptotes, the square root function does not have any asymptote. They would either be horizontal or vertical.
Uh,
Okay, so this one actually has none. The log function has a vertical asymptote at x equals 0.
Got it.
Okay, so you might say x equals 0, vertical asymptote. And then end behavior. Okay, so this is as x goes to infinity, meaning to the right. So let's go back up to the graph and imagine tracing it to the right. If you were to trace this graph to the right, what happens to the y values? What happens to the y values as you go to the right?
Um, they increase.
They increase. So f of x or y goes to infinity. And then for going left, see, it doesn't go left forever. It just stops at 0. So there's not really end behavior. There's sort of kind of end behavior. It depends on how your instructor looks at this. So I'm not sure there's end behavior going the other way. But for the logarithm, we can do the same thing as x goes to infinity, as x goes to the right. So we're gonna look at this graph over here. As you traverse the curve to the right, how far up does this go? I know it looks like it goes more horizontal, but does it go up to infinity? Yes, it does. Okay, so as x goes to infinity, f of x also goes to infinity. But this time we can go the other direction, kind of. Kind of. So I guess we do have to add this in as x goes to 0.
Does x go to 0?
So as we're going the other way and going down, what happens to the y values? They go down.
They go down, but x does not go to 0. There's a little curve, so it won't be.
It approaches 0. So you can say it as it approaches 0, f of x, which is the y, approaches negative infinity.
Okay.
And then on the other side here, I guess we can say as x goes to 0, f of x this time, if we look at the other graph again, you can see that as x goes to 0, it actually hits 0, goes right there. So f of x goes to 0. All right, now we can probably answer what's the same and what's different. There's not a lot that's the same. I mean, you can kind of say that the graphs are kind of the same, kind of. I mean, I don't really think they're the same, but they maybe be the same. Domain is kind of the same. And then ranges are different, asymptotes are different. End behavior and going to the right is kind of the same, but the left is not. So the first row is to the right, the second one's to the left. So in terms of what to put for number 1, if you're
Yeah.
being really legalistic, you would say just the end behavior on to the right. But you could probably also add in the graphs look similar and the domains are similar.
All right.
Now, in terms of what's different, well, there's a lot that's different. You can say the ranges are different. That's number 2. The asymptotes are different. And the end behavior to the left is different.
Sorry, I'm just writing it down.
Take your time. Make sure it's clear. Yeah, for the person reading it. Be great, the instructor.
All right, I got it written down.
Okay. So do you feel like you have enough down for 1 and 2?
Yes.
Okay, because we are going to do the same thing for 3 and 4. For 3, we need the graph of log x, which is, oh, you know what we did not do is we did not do intercepts. So we should add those real quick. Why they give these laundry lists, and they really need to do a better job
Wait.
organizing. So intercepts, the square root of x has an x-intercept and a y-intercept at 0, 0. So we can say that x comma y intercept at 0, 0.
Are we on 3 now?
No, this is a continuation 1 and 2. This is more information.
Is that why you called them a laundry list or something?
Yes, that's why there's way too much here. They don't organize it well.
Sounds like you're trying to make a schedule.
Kind of, yeah. So the other graph here, it's hard to see, but at 1, 0, there is an x-intercept, but
Mhm.
not a y-intercept. It never crosses the y-axis. So we would say that down here, we would say no y-intercept, but we would add that there's an x-intercept at 1, 0.
It. Okay.
All
Oh,
right, so for 3 and 4, we are doing something similar. Graph. These have more similarities. So on the left here is log x, and on the right here is natural log of x. Kind of do the same thing here. We'll just go through all of these again, and we'll talk about the similarities and the differences at the end.
okay.
So the graphs kind of look the same. I haven't drawn them in the same scale, but they look pretty similar. That's a good thing. The domain is actually the same for both. It's 0 to infinity.
Mhm.
This is a good thing. Can you tell me the range for one or both of them, please?
Okay, I'll do the first graph.
Okay.
The range would be 0, negative infinity.
So if this were true, okay, if this were true, 0 is the smallest value.
Yes.
Okay, and you have to think of it as how far down is the graph going? How far down does the graph go?
Okay.
It goes further than 0.
Mhm.
How far down does this graph go? We did this actually in the previous problem. If you want to look up and see.
All right, which previous problem should I look at? Okay, there. I don't have those graphs written down, but I don't know why I don't. I'm sorry.
That's okay.
Hmm. Okay, then it
So
would
the
be
one,
0, 0 for the first graph then, right?
but we're looking at the graph on the right. The graph on the right is log of x.
Okay.
How far down does it go?
Goes down negative infinity to positive infinity.
Right. So the range for the one on the left here is minus infinity to positive infinity. What about for the one on the right? How far down does this graph appear to go?
It appears to go from a 1, negative infinity.
How far down? Let's just start with that. How far down does this graph go?
It goes down till like infinitely. Like
Okay, negative infinity.
yeah.
And then you need a little bit of help because you just wouldn't know unless you looked at this before. But this graph, even though it looks like it goes more to the right, it actually goes up forever. It goes right and up forever. So how far up is forever? Or what does up forever mean?
Went up forever. That's infinite. That's
Yeah,
infinite. Positive.
yes. Good. These have the same range and the same domain. That's good. Asymptotes now. These both have a vertical asymptote at x equals 0. So graphically, it looks like this. There's a vertical line that it approaches.
It's
All right, so they have the same, these have a lot more similarities. Intercepts now. These both have an x-intercept. Kind of hard to see, but it's at 1, 0 and at 1, 0. So they both have an x-intercept at 1, 0.
okay.
The y-intercept occurs if it crosses the y-axis. But the graph just approaches the y-axis and goes down forever and ever and ever. It never crosses. Same thing on the one on the left here. It goes down forever and ever and ever, but never crosses. So this has no y-intercept.
Got it.
Right. And then the last thing is the end behavior. As x goes to infinity. So this means to the right, as we're going to the right. So you go back to the graph, always go back to the graph here. As you traverse the curve to the right, how high up does this go?
It goes up infinitely.
That's right. So we can say f of x goes to infinity. And then similarly, as x goes to 0 on the left here. So we're going to go back the other way. So as you go back the other way in the curve, how far down does it go?
Goes down negatively.
To negative infinity, yes. And then the one on the right is exactly the same. So these have way more similarities than differences. Basically, everything about them is the same, right? Graphs are the same, 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 same. But they're not exactly the same graph. They're just really, really similar.
Okay,
But
got it. Graphs are great.
they do help. They really do. Be able to see something as
I enjoy using graphs. It's just that now they're so complicated. I don't like them anymore.
they are, yeah.
But I still like them. So it's a love-hate relationship, I would say.
All right. Well, we'll go ahead and get those down. We are going to do more graphing for problem 5.
So we're doing 3 and 4 at the end, right?
Well, yeah, 3. Sorry, just to be clear, I guess you're not able to see it. 3 is to state the similarities, and 4 is to state the differences.
Yeah.
So the everything is the same. You can go through this entire list, say everything's the same. The difference you should say is that the graphs are not exactly the same. In fact, I'll graph them, overlay the graphs so that you can see the difference.
I'm sorry. It's just that like you were saying so much, and I got lost, and I was like, okay, hold on, I need to re-ask my question. I'm so sorry.
All right, so just to keep in mind, they're not exactly the same graph. Here we have the graph shows. The black one here is the natural log of X. The red one is log of X. You can see they're not exactly the same graph, and that's probably the main difference. You can say that they're not the same graph, but they have all the same characteristics.
Mm-hmm. Okay.
So if that's sufficient, let me know. We can go on to number 5.
Yeah, I'm ready for number 5.
All right.
Sorry for like asking that question. I got kind of lost.
Yeah, the next questions are a little more
They're a little more tricky.
I think they're more straightforward. 5 we've actually done here. We've actually done this, but we have to sort of fill in some of these same things again. So the graph of log is this one here. So I'll go graph it again, grab the graph of it. So the domain we already have. Domain is from 0 to infinity. The range is minus infinity to infinity. The asymptote is x equals 0. And the intercepts, the only x-intercept is the x-intercept at 1, 0.
Okay.
Now to graph it, so let me go see what they do in example 1, because I don't know how much they want you to do here. Yeah, so it looks like they want you to just go to Desmos and graph it.
Yeah, let me guess. You said you got to upload all your pictures from Desmos, right?
Probably. I mean, I haven't really been looking at the requirements. I
Oh,
guess I would get a graph of something like this.
it's I just read the directions. The teacher said you can either upload a photo from Desmos or you can graph it by hand. I am gonna
Okay.
graph by hand because I like graphing by hand.
All right. Well, she needs something that looks like this, and that should be sufficient.
Yeah. Okay, I'm ready, by the way. For number
All
6.
right. Okay, so for number 6, I'd like you to graph this for us. Go into the calculator just to get an idea of what it looks like.
Okay.
I'll do the same. We can compare results. Now to do this base 2, I believe there's a function for that, but you can also use the underscore if you get stuck on that from the keyboard. I think the keyboard though has it under functions. It does. It does. So under functions, if you scroll down to calculus, it will show you log with a little a.
You said in which one exactly?
If you click on the functions button, you'll
Yeah.
see a little drop down thing. And if you scroll down to where it says calculus,
Okay. Oh,
so
log with an A. Yeah, I see it.
I see it right there.
Okay, I got the graph.
Fantastic. So the key characteristic of the graph that you're looking for here is does your graph go through that point 4, 0?
Yes.
All right, so you got it then. Very good. So the domain is yet to change. It goes from 0 to infinity.
All right.
The range, though, is how far down does it go?
Um,
How far down does your graph go?
from negative infinity.
Okay, good. Goes down to negative infinity. How far up does it go, even though it looks like it's going
Positive
more to the right?
It goes
Positive
down.
infinity. Yeah. So this is minus infinity to infinity.
Okay.
Okay. How about asymptotes? Where does it cross the x-axis?
Where does it cross? 4, 0, right?
Yep. I'm sorry, that's the intercept. I'm sorry, that's the x-intercept. We will come back and do the asymptote.
The asymptote crosses.
The asymptote is this vertical line here at 0, x equals 0. It's the line that the graph approaches.
It crosses like near negative, like negative infinity, right?
Yeah, there's no, it doesn't cross it. It just keeps going down forever.
Okay.
So you'll need some sort of a reasonable sketch of this curve, and then labeling the information. A lot of this is the same each time. We're not really talking about why, but maybe we will in another problem. Like number 7. Yeah, number 7 is slightly different.
Mm-hmm.
Okay, so let me know when you're ready. We can move on to number 7.
Yeah, I'm ready for 7.
All right, so go ahead and graph this for us, please.
Okay. All right.
Where does it cross the x-axis this time?
Like 3, 0. No, sorry. No, wait. Yeah. 3, 0.
Yes.
Supposed to say 0, 3. I'm like, no, wait. That's not right.
So this one's a little bit different. It's actually the whole graph is moved to the right,
Yeah.
and x equals 2 is the new asymptote. It's the thing that it's like the graph is like bumping up against here. It never crosses this line now. And that affects the domain. The domain, like normally we start at 0 to infinity, but it actually starts at the vertical asymptote. So in this case, the domain is 2 to infinity.
Mm-hmm. Got it.
How about the range? Does the range look any different this time?
No.
No difference in the range, minus infinity to infinity. And how about the intercepts? Do you see any x-intercepts?
It would be 3, 0.
Got it. And you might say no y-intercepts. Right, so number 8. Number 8 is slightly different. It's no longer log, it's using ln. Okay, so you can either type ln when you graph it, or you can go find that calculus function again, but I would just type ln.
All right.
Go ahead and graph it, and I'll do the same.
Okay.
The graph kind of is upside down from what we're used to. Do you see that?
Yeah.
But it still kind of has some of the same key characteristics. And instead of going like down forever, it goes up forever. And it still goes to the right forever, but it also goes down forever. And you can see here, it still has a x-intercept of 1, 0.
Mhm.
All right, so domain is unchanged. It's 0 to infinity. You see that it approaches this line right here, which is x equals 0. Range, how far down does this go over here? Does it go down forever?
Yeah.
It does. So we can say minus infinity. And then if you go the other direction, it goes up forever.
I feel like the range in most of the graphs it never changes.
That's right. It's actually in all logarithm functions, it's minus infinity to infinity.
Are there rare occasions that the range can change?
Not for a logarithm. It's always minus infinity to infinity.
All right. I was just a little curious, you know.
Yeah, there's a relationship between exponentials and logarithms that they're not kind of showing you yet, but it is the case that the range is always this. It's always minus infinity to infinity.
Mhm. The asymptote, I'm gonna just first say is x equals 0.
Again, yep, that's true.
And then the intercept is 1 comma 0.
You got it.
Right? Number
All
9.
right, number 9. Okay, so number 9 is one of the first kind of multiple choice questions that we've seen besides the reviews. So let me snip it in here. It says, Joe, how you use a t-chart to determine which of the following is a graph of e to the minus 2x. Okay. So let me just look at the graphs here. All right, here we go. So here's what you have to do. You have to put in 0, 1, and 2, maybe 3 into e to the minus 2x.
Mhm.
So you want to go to that's most scientific.
Okay, let me first pull up the scientific because I'm in the graphing one. Okay, there we go. Okay, I'm ready.
So you're going to put in 0 for x. So it's e to the minus 2 times 0. You'll probably need this to be in parentheses. Make it work.
2 times 0, negative 2 times 0. The answer for that would be 1.
Now do the same thing for 1.
Okay. That'd be 0.1, 0.14. I don't know if I round up.
That's fine. I'm gonna, yeah, however many decimal places is fine. Now do it for 2.
0.018.
Okay.
Yeah.
All right. So now I snip in some graphs and you decide which one has those same numbers on there. So here's and again, like you could exclude some, like if you say, oh, those don't look at all right. Let me get these better in here. Okay. So like the first one is 0, 1. Which of these graphs has the ordered pair 0, 1 and A, B, C, or D? Which one has 0, 1 in it?
The C,
And which else? Which other one?
C and A.
A, this is 0, 1. I'm sorry, that's 0, 0. Sorry, 0, 1 is up above it. Let the graph go through 0, 1.
Then I don't know what the second one would be.
Well, it's not A. And C does work, so it's down to either B or D.
I don't think it's not B, so it has to be D.
Okay, so there's the point 0, 1, and there's the point 0, 1. Okay, the next ordered pair was 1, comma, 0.1353. Which of these has that point? Or which one doesn't is the other way to look at it.
Okay, give me like 1 second. Okay, so let's see. B would work, maybe.
Which one? I didn't hear.
I said B, but now I'm not sure with my answer.
Well, we can't, it can't be A or B because we've already crossed those out. We're looking at these two graphs, C and D. Which one goes through the point 1, comma, 0.1353? You know, X and then Y.
D.
D, yeah.
Whew.
Okay.
My lucky.
All right, so that takes care of that. So you do have to, in terms of like how you answer it, you have to show the T-chart, and then I would probably show a quick graph of these. I guess I would show the one that's correct, you know, show something like that. Or just say graph D as well.
Yeah.
Oh, you know what? There were two more graphs. So
Graphs really don't like us, man.
you're in luck. It looks like it is graph D. So
Yeah.
all right, here we go.
I know my graphs. I know my graphs.
Last problem here. All right, so here we go. Gonna snip this one in. All right. The graph in example 2 above illustrates a logarithmic model of years as a function of the balance in a bank account. So we got to go find that. I'm going to go find example 2. Scrolling up. EX1, EX2. Okay, let me actually zoom out a little. Oh, that's all they give you. Okay.
I need a new page. Okay.
All right, so they give you this graph in example 2. Okay, and it says how many years will it take to have $3,500 in the account. Okay, and if you go back to example 2, example 2 is a different number, but the way that they do this in example 2 is they go to 4,000 because example 2 is about 4,000. They go straight up until they hit the curve, and then they go straight left.
Okay.
So that's the example, and that's about 10 years. So you have to do the same thing. I know you don't have this in front of you, but you sort of want to, for 3,500 years, you want to find that on the x-axis here, go up until you hit the curve, and then bounce left, straight left.
So like it take approximately like 10 years to get $35,000.
And then the example is 4,000. That's
Right.
the one that they give you an example to, and you can see it hits up at about 10 years. Okay, but your problem is 3,500. So you have to start your line at 3,500 and decide where it hits the graph, and then go left, go straight left.
Got it.
It's not 10 years. It's less than 10 years.
Okay. Okay, if it's less than 10 years, so that means, well, it depends on the job, first of all. Let me,
Again, you're just going up until you hit the curve. I'm trying not to do everything for you here. Then you go
so,
straight left, straight
so
left.
it would take like approximately like 7-ish years
Good. That's a reasonable answer.
because it's in
7 years.
I was about to say 5, and I was like, wait, what am I looking at? Yes,
Well,
so
there's a reasonable answer like 7, and then there's unreasonable like 5. 5's probably too small. 8's probably too big. 6 might be okay. Just depends on kind of,
I think for my answer, I'll write 7 to 6 years
okay.
because when you look at how when you drew the line and how it curves, it's closer to 6. So I'll say 6
Sure,
to 7 years.
sure.
Yeah.
Good. Okay, so this is a good place for us to stop for today. Lesson 26 and 27, more graphing. If you have some time, it'd be great if you could look those over.
Yeah.
Maybe even do the stop and think questions and see how you do. Looks like tentatively we would finish those this week, and then next Monday we would be able to start on lesson 28, the review lesson. And then next week, there's the possibility of finishing everything in unit 5. And then the following week would be finishing up unit 6-ish. So still on schedule. I think you're doing great. We're going to go ahead and stop here for today.